Unutmadan yoklamaya başlayabilirsiniz. Çıkarır. Yoklama. Şimdi kağıt çıkarabilirsiniz. Evet, başlayabiliriz herhalde artık. Okay, so last time I started cache organization. We said that main memory is slow to access. Therefore, in order to execute instructions in a faster way, we need a faster type of memory between the main memory and the CPU. And very frequently used data or instructions are kept in the cache memory. And if the memory address that the CPU is trying to access is in the cache, if it were already in the cache, in that case, the CPU can access it in a very fast way. But if it is not in the cache, it must come from the main memory into the cache and then to CPU, so that from the main memory we bring it into the cache, because the next time we access a closer address, an address closer to the current address that we're accessing, it will be the probability of having it in the cache will be high. And we said that the data moves from main memory into the cache in the form of blocks, and from the cache, one word is transferred to the CPU. So our aim is to increase the hit ratio if the hit ratio was the number of hits. The number of times we find the data in cache is called a hit. And if we are doing, let's say, 100 accesses to the memory, if let's say 90% of it is in the cache, then it means we have a good hit ratio. And to access the data in the cache, to place the data, to place blocks in the cache is called the mapping operation, where in the cache, if the block is being moved from the main memory into the cache, where will it be placed in the cache is called the mapping operation. And we said that there are three basic mapping techniques. And I explained direct mapping. Let's remember direct mapping. Here, each block has a specific place in the cache. So this is determined according to the mode operation. If a block number, the block takes the block number and find its mode according to the number of lines in the cache. So in this example, we take the mode of block number to 4, because there are 4 lines in the cache. So therefore, according to this, block 0 will be mapped to line 0, block 1 to line 1, block 2 line 2, block 3 line 3, and then again mode 4 of block 4 is again 0, so it's also mapped to line 0. Therefore, the blocks 0, 4, 8 and following blocks are mapped to line 0 always. Block 1, 5, 9, their mode with respect to 1 is 4 is 1, so they are mapped to line 1. So at any time that there is a data, there's a valid data in the cache, maybe, let's say, assume that we are checking line 0. There may be more than one block that are mapped to that line. But at any time, when we check that line, how can we determine which block is it? You remember, we divide the address that the CPU is trying to access into tag, line, and word fields. The rightmost bits, word field, the address shows which word it is in the block. In our example, we assume that there are 4 words in a block. So therefore, in this block, there are 4 words. And the addresses of those 4 words, the rightmost 2 bits would show 0, 1, 2, 3. So if there are 4 words in a block, then 2 bits are enough to address those words. But if there are 8 words in a block, in that case, from this address, memory address, rightmost 3 bits will be used as the word field. Then comes the line field. The line field determines to which line the block will be replaced. If we consider the block number, let's say block number 2D, in that case, this is block number in binary, 2D. There are to check where it will be mapped in the cache, I must use the mode operation. And the mode in binary numbers, you remember, is easy because if you are taking the mode of 4 is 2 to the power 2. So you take the rightmost 2 bits, and that is the mode, the result of the mode operation. So that's why after the word field, these two, I have not selected them. These 6 bits are the block number, and mode, according to the mode operation, the rightmost 2 bits will show its line number. So it will be mapped to line 1. Now that block will be mapped here, but to line 1, many blocks can be mapped. It may be block 1, block 5, block 9, or some other block, and also block 2D is mapped to line 1. So how can we check if this is block 2D or not? There is the tag field. For all the blocks that map to the same cache line have different tags. This is the leftmost bits that are the address. After the word and line fields, the rest is called the tag, and that is different for each block that maps to the same cache line. Therefore, the tag is this one. So the CPU in direct mapping, the CPU checks, this is the same example, the CPU checks, finds the line field, finds the line field, goes to line 1, and compares the tag in that line with the tag in the address. And if the 2 tags are the same, this means that block 2D is already in the cache. So it is a cache hit. This comparison circuit will compare the 2 tags, and one of these lines, either a hit or a miss line, is set. One is set, the other one is reset. So if it is hit, it means that the block is already in the cache. If it, in that case, it access the word 3 using this word field, it will access word 3, which is this word, the last word in that block, and send it to the CPU. But if it is not in the cache, assume that another block is here, or the cache is empty. It's the first time we switch on the system. In that case, the block 2D, although it's trying to access, although the CPU is trying to access a single word, the complete block comes into the cache, and then word key is selected and sent to the CPU. So this is a simple method because each block has a single line to be mapped. Therefore, the comparison circuit is not too complex because we know which line the block can exist. Therefore, we compare only the tag of that line with the tag address. But there was a problem, you remember, in direct mapping. Because if more than one word, more than one block that map to the same cache line continuously replace each other, in that case, it is a performance problem. So let's remember these two addresses. Assume that the CPU first tries to access this address, V7. And then it tries to access 04 address. And then it repeats that continuously. Load V7, load 04, load V7, load 04. Now, as you see, the two words, V7 and 04, are both mapped to the same cache line 01. So when in this load instruction, block, let me see the block number. Onları yazmamışım ama bu block 2D'de this is V7 in block 2D from the previous example, and address 04 is in block 01. This is for 04. It is in block 01. So now, therefore, first block 2D will be accessed. It will be taken into the cache, and then in the next instruction, block 01 will be moved into the cache. So block 2D is not anymore in the cache. It is replaced by block 01. And then the CPU is trying to access block 2D. Again, now block 2D will replace block 01. Then again, block 01 will be accessed. So that will replace block 2D. So actually, these blocks will continuously replace each other. So what is the performance problem here? The problem is we are trying to access a single word, but from the main memory, a block comes into the cache. So it's not a single word, 4 words will come into the cache. So it takes time. And we use only one word from the cache. Again, 4 words are moved into the cache, but we use again only one word. So actually, this will decrease the performance because we move the complete block into the cache just for one word. In this case, direct mapping has a disadvantage. How can we eliminate that disadvantage? If both block 2D and block 01 can exist at the same time in the cache, then we don't need to take them from the main memory every time we try to access. So that is possible in associative mapping, the second type of mapping strategy in cache organization. Here, in associative mapping, a block is mapped into any location in the cache. So you remember, in direct mapping, each block has a specific location in the cache. It cannot be mapped to anywhere else. But in associative mapping, we say that any block can be mapped to anywhere in the cache. So, for example, we take block 0 here in line 1, and then assume that block 5 is accessed, take it to line 1, then block 6, take it to line 3, and so on. So, in this case, both block 01 and block 2D can exist in the cache at the same time. They may be mapped to different cache lines, whichever cache line is free. Now, let's take the same example. Now, associative mapping. Here, we don't have a line field because a block can be mapped to anywhere in the cache. First, the CPU was to access ED7, which is in block 2D. So, take it into the cache. Let's assume that the cache is empty. So, place it in line 0. Now, here, the tag, again, the rightmost 2 bits are the word fields. So, again, we assume that there are 4 words in a block. And the rest is used as the tag. So, this is the tag for it. Now, after that, CPU is trying to access address 04. That is in block 01. So, go to the cache. Let's assume that line 1 is free. So, place block 01 here. Again, the tag is without line field. Tag is this part. If after that the CPU is accessing B7, it is already in the cache. This is here. So, no need to take it again from the main memory. Also, then it accesses block address 04. It is already in the cache. So that will increase the ratio because after the first time they are accessed, they are put in the cache, and then the next time they are accessed, the same addresses, they are already in the cache. So that will increase the performance of the system. Do you follow? Tabii. L0, L1 şunları mı? Neden L0'a koyduk bunu? Yani diyelim ki sistemi ilk defa açtık. Cache memory'de valid bir şey yok. O zaman ilkini yazabiliriz. İlk boş bulduğumuz yere yazabiliriz. Okay, now let's talk about the cache circuitry, because now if we are looking for a block in direct mapping, we know each block has a specific place, so we only go to that. Önceki slide'a geçelim. We only go to that line and compare only this tag with the tag in the address. Because this block cannot be anywhere else in the cache. It can be only in line 1, in the direct mapping. But in now associative mapping, a block can be anywhere in the cache. So therefore, in order to check if the block is already in the cache or not, we have to compare all the tags in the cache with the tag in the address. Because it can be anywhere in the cache. So therefore, associative mapping, the comparison circuit is much more complex because now this tag in the address must be compared to all the tags in the cache. So this comparison must be done in a very fast way because we are using caches to increase the performance. If we do this comparison in time-consuming methods, it will not increase the performance. So, as the name implies, this comparison circuit is an associative memory. Do you remember associative memory? In associative memory, we design a circuit for each bit, to check if it is equal to a given argument. Here, our argument is the tag in the given address, and this tag field here, and these tag fields are the contents of the associative memory, and that comparison hardware will compare this tag by all the tags in the associative memory in one step. So this is one use of associative memory in cache organization. So now the problem here is we need to construct a very complex hardware to do the comparison. As the comparison hardware is too complex, the size of an associative map cache cannot be too large. That is the disadvantage of it, because you need a data storage area, and also you need a complex comparison hardware, so that the size of that type of cache cannot be too large. But hit ratio is the highest because you can find different blocks that are required to be accessed in the cache at the same time. They don't replace each other. Evet, online grupta soru var mı arkadaşlar? Peki, devam ediyoruz. Okay, now what will happen if, okay, we're accessing block 2D, and then we're accessing block 01, and then we're accessing block 5, then we're accessing A2, block A2, and after some time, the cache will be full. What will happen? When the when the cache is full, after, if I'm trying to access another block which is not in the cache, one of them will be replaced. But which one shall I replace? İşte ama işlemcinin onunla işinin bitip bitmediğini bilmiyoruz. Yani daha sonra ona erişmek isteyecek mi CPU bloğa? Eğer daha sonra erişmek istiyorsa onun cache'te durması performans açısından daha iyi. Ama daha sonra erişmeyecekse onu replace edebilirim. Ama daha sonra erişmeyeceğini bilme şansım yok. Çünkü programın ileriki aşamaları hakkında bir bilgim yok aslında şu anda. Dolayısıyla bir tanesini replace edeceğim ama ihtimal, yani probability üzerinden giderek, yani bunun daha sonra erişilme ihtimali daha az olanı seçip replace etmem lazım.
Hocam, peki hepsinin erişilme ihtimali eşitse ne oluyor? Yani ilk bulduğu en uygun yeri mi siliyor?
Tabii bir tanesini seçecek, yani ikisinin de erişilme ihtimali aynıysa birini seçecek, yani random da seçebilir öyle bir durumda.
Tamamdır hocam, teşekkür ederim.
Okay, so that is called replacement algorithms. When the cache is full, if a new block is to be read into the cache, one of the existing blocks must be replaced. We said that. And one of the methods is called round robin, or first in, first out. So here, the first one that is placed into the cache is the one to be replaced first. So let's see in our example, block 2D, and then accessing block 01, and then two more different blocks, and the one that has been brought into the cache is block 2D, so that can be replaced. So the first in, first out replacement selects the first one that is placed into the cache, assuming that it is the first one that is put in the cache, and the later ones will be accessed in the future. That is the assumption. So the first one that is placed in the cache is replaced. There are other replacement algorithms I will explain later, but the simplest one and this one is this. Now the third method is combines the advantages of these two methods and eliminates the disadvantages. So in direct mapping, we said that it is simple. A simple comparison circuit is required, and therefore the size of the cache may be larger. In associative mapping, the heat ratio is higher, but the size of the cache cannot be too large. The third method is set associative mapping. Here, we have in direct mapping, let's go back to direct mapping. To this example, where two blocks continuously replace each other. So if I can keep, the two blocks map to the same line. If I still map these two blocks to the same line, but in the same line, if I have another storage area here, so if one block is in this part and the other block is in the extra, the added storage area, both of them will be mapped to the same line, same place, but in two different, they both can exist in the cache at the same time. Şey yapabildiniz mi? Takip edebildiniz mi? Yani burada ikisi birbirini replace ediyor. Çünkü bir tek yer var. Ama iki tane storage area ayırsam aynı line numarasıyla o zaman ikisi de aynı anda cache'de olabilir. Değil mi? So that is actually the idea behind the set associative mapping. So here there are sets. Each block has a specific set number. This is determined according to the mode operation. But in the same set, they can be mapped to different lines. So for example, block 0 and block 4 are mapped to the same set 0 according to the mode operation. But one of them is mapped to line 0, the other one is mapped to line 1. Again, block 1 and block 5, according to mode operation, are mapped to set 1. One of them is mapped to line 0, the other one is mapped to line 1. So, the comparison circuit is not too complex because they have specific places in the cache, but in two different lines. So the comparison circuit will compare only the tags of set 1, not the other tags. And the advantage is the two blocks that map to the same set can exist in the cache at the same time. So let's come to our example, block B7 and 04. There are 4 sets, and in each set there are 2 lines. Now block 2D is mapped to set 1. Block 01 is mapped to set 2. Again set 1, but one of them is mapped to line 0, the other one to line 1. So in this way, if in the program they are accessed one after the other. They both are in the cache at the same time. So after the first access, the other accesses will be hit. Now they will not replace each other. About the comparison circuit, we know that they cannot be anywhere else in the cache. They can be only in set 1. So just to compare the tag in set 1 and set 2 with the tag in the given address. So in this way, let's see the comparison circuit. Only the tag of this set will be compared. So the comparison circuit will not be too complex, like associative mapping. But the performance will be much better than direct mapping because 2 blocks can be found in the cache at the same time. Okay, I want to talk about this hardware now. Let's see the direct mapping hardware. Here, this is for direct mapping. Again, forwards exist in a block. So this is the address, memory address. It has word, line, and tag fields. As there are forwards in the address in the block, 2 bits are required for the word field. And assume that only 12 bits for the line field. And using this line field, it accesses to a line in the cache. So this is the cache. There are 1, 2, 3 forwards in one block. That's the data area. There is the tag area and a valid bit area. Do you remember valid bit? If when you switch on the computer, everything is invalid, but after you place something valid data comes into the cache, it becomes valid. That means 1, and that is after that time it's always valid. So the system has to compare. Okay, the system uses the line field, this is one, from the given address to access that line. And then it takes the tag from that line and compares the tag that is given in the address to check if they are equal. And it also has to compare the valid bit. If the valid bit is 0, there is no valid information even if the tags match by chance. So if valid bit is 1 and this comparison output is true, they are the same, then it's a hit. So in that case, use the word field to access that word. How does it work? The word field is a 4-bit. There are 4 words, so there are 2 bits for selection. And there's a multiplexer here. You remember multiplexer? Set. The multiplexer has select inputs. And if this word field is, let's say, 3, then word 0, 1, 2, 3 comes to the multiplexer, but it will select only word 3 and send it to the CPU. Right? So that is the basic hardware for direct mapping. Now let's see it for set associative mapping. Here we have a 4-way set associative mapping. Let me talk about the 2-way, 4-way. Now, in set associative mapping, we call it either 2-way, 4-way, 8-way, or more, but usually not more than 8-way. So this means that Okay, the blocks are mapped to the cache according to mode operation to one of these sets. And there are, in this case, there are 1 and 2 lines. So that is a two-way set associative cache. But instead of 2 lines, if there are 4 lines, if I add 2 more lines, it is 4-way set associative cache. So in a given set, how many possibilities that I can place the block in the cache? That is that 2-way, 4-way, or k-way. So if k is equal to 1, there's only one line, only this one, that is like direct mapping. But if k is equal to v, it should be k is equal to v. Yanlış yazılmış. If k is the same as the number of sets, so in that case there's one set and v number of lines in it, so it can be mapped to anywhere in the cache. So it is like associative mapping. Now let's come to this example, hardware. Here there are 4 lines, 1, 2, 3, 4.
Ben bir şey sorabilirim burada.
Efendim?
Buradaki diyagramın fikriniz olmasa mı başka mı soruyorsunuz, yoksa buradaki oraya kapılarını falan ileride kullanacak mıyız? Ya da sırada vesaire kullanacak mıyız?
Kullanabiliriz tabii.
Tamam hocam.
Okay, there are 4, it's 4-way, there are 4 lines, 4 possibilities for a block to be placed. And this index is the set number. That's the valid bit. So using the set field, we go to the same set. So the block may be here, there, or there. So in this example, there are 1 word for per block, or you may see that as a block. Okay, now the comparison circuit is required to check these 4 tags at the same time. So check if they are equal, and also these bits are true. So only one of them can be equal. The others can either none of them is equal, or only maximum one of them can be equal. So assume that this is equal and the others are 0. This comparison results as 0. So this OR gate takes the results of these AND gates. That means it checks if anyone is true. In that case, it's a hit. If anyone matches, it's a hit. If none of them matches, then it's a miss. So hit line will be 0 in that case. So here, the OR gate will result as 1. And which data will be sent to the CPU? You see this one, it's connected to this line. So it will select, this again is a multiplexer set, and it will select this word, is sent to CPU. So that is the hardware for a simple 4-way set associative organization. Any questions up to this point? The online group? Okay. Devam edelim mi? Tamam. So now we said that the cache, okay, each block has a specific set to be mapped, but it can be mapped to any of these lines in the cache. Now the problem is, again, we map a block here, another block there, another block there, another block there, and if another block will be mapped to the same set, so one of them must be replaced. Again, the replacement algorithms are required. When the cache is full, if a new block is to be read, some of the blocks must be replaced. And the replacement algorithms are implemented by hardware. So which one will be replaced? This selection is done by the hardware. So in direct mapping, there is no replacement because each block is mapped to the same cache line, to a specific cache line. Now, in associative and set associative mapping, I already explained first in, first out. First in, first out chooses the block which has been in the cache the longest time. So the first one that is brought into the cache is the first one to be replaced. Another replacement method is random replacement. Here, one of them is selected randomly. And it was found that the performance of random replacement is not worse than the others. Now there are two more replacement algorithms. Least recently used and least frequently used. Least recently used means if I have used a block recently, I assume that I will use it later in the later computations. But if I haven't used the block for a long time, I will assume that I will not use it in the future. So this is takes the time into consideration, but least frequently used checks how many times I'm accessing a block. If I access a block very frequently, then I assume that in the future I will access that block again. But if I don't access a block very frequently, then I will assume that I can replace it. So for the least recently used, if I use a block recently, then I will use it again in the future. In a two-way associative, set associative cache, you use a use bit. If there are two lines, either it is in line 0 or line 1. If I access line 0, this is the one that I accessed recently. So I set the use bit of line 0 to 1, and the other use bit 0. If I access line 1 in the next time, so I recently now accessed line 1, the other one is not recent, so set it to 0, line 1 set it to 1. So in this way, only one of these lines is recently used, the other one is not recently used, so replace that, which is not recently used, which is the one used with 0. When we come to least frequently used, for each line, I need to keep a counter. The counter will count how many times I have accessed that line. And when I have to replace it, I compare the counters. The one that has the lowest counter will be replaced. So the one with the highest counter will have the most frequently used one. So replace the one that has the lowest counter. So that's the counter associated with it. Here, I try to explain the two methods by an example, but I don't think that we have time for it. Buraya kadar sorunuz var mı arkadaşlar? Yoklama aldık mı? Ulaştı mı? Yok, bu önceki dersin yoklaması. Tamam, değil mi? İmzalamayan yok. Peki, o zaman devam edeceğiz. Hepinize iyi günler. Online grup aydınlayın. Bir dakika yoklama alacağım. Şimdi herkes lütfen here yazarsa sevinirim. Here yazdıktan sonra çıkabilirsiniz. Hepinize iyi günler diliyorum.